All right, so we have an exam tomorrow. Hopefully that is not surprising to people. So I noticed how the last exam went. So what I am going to be doing, I made a slide deck with some exam 3 practice problems. And I want to first address questions that people have, but then we can go over some of these questions that are of a similar nature to what I might ask on the exam. So let's start there. Does anyone have any questions for me to answer? While we do this, I don't think these are animated correctly. They are. No questions? We're feeling super confident, or are we typing a question?
So if we're asked to say a set is uncountable, what constitutes as like enough reasoning to say that it's not countable?
You would have to provide an argument that says that there is no such enumeration that we could do. So you could use something like Cantor's diagonalization to be able to say, assume that we had an infinite list of the elements of this set. Could you provide an example of an element that's not in that list? And then could you argue that no matter how you list that set, there is always going to be some counterexample of something that's not in the list? Or that you would never get to, even with the most intelligent algorithm you could think of. I do have some examples of that we can go over at the end of this, but that's a great question. You could do that, or you could do some kind of reduction if you wanted to try to write down a reduction and say, if we could enumerate this set, then we could solve the halting problem or some other element like that. I won't make that a requirement. I won't make that the easy way to solve a problem, but if that's the way that comes to you in an exam, that's certainly a tool that we have talked about. No questions from either people online? I guess I will go into some practice problems. So the first section of questions that I might ask you that I would think might be a bit of a struggle. Design a Turing machine to remove the first A from a string over AB star. So on the tape are some number of A's and B's. You want to remove the first A.
Do we want to like shift everything else over to just
Yes.
blank? Okay.
Yeah, we want the answer to be on the tape. So we want the new string to be on the tape when we are done. Here's where I would assume people are going to at least be able to hopefully get. So if we see a B, we want to read the B, write the B, and move right. So just continue to do that until we reach an A. Once we do that to that A, what do we want to do?
Mark it with something outside of the alphabet. So just like an X or something.
Yeah, we could do something outside of the alphabet for the moment, but let's make that an X for the moment. That says we read it and we're going to move right. We want to stay in Q. Yeah, so we're moving to Q1 because now we have this new set. So now we want some set of instructions that are going to move symbols left. So that's what Q1 is going to try to do. So now we have a string, maybe we had some B's that we moved to the left over. We saw our first A that we marked with an X. And now whatever comes after this, we want to shift it all backwards. So what sets of instructions can we write that are going to do that?
We can look for a non-blank character, and we can have two new states, one for if we found an A, one for if we found a B.
Yes. So in Q1, if we see an A, we want to write it as an X, right? Because we're going to be writing to the X when we move. So let's say we're going to move to a Q2 that tells us that we read an A, and we're going to write an X, and we're going to move left to go backwards to the X that was there. So from Q2 now, if we read an X, then we want to write an A and move right. But do we want to stay in Q2?
No.
No, because if we did that, then we'd see an X again, and as soon as we moved right. So where do we want to move to? What would make sense there?
Say back to Q1.
Q1. So that tells us that we're still trying to look for the next symbol to move. But that means we need to write, what are we going to do for Q1 on an X?
Just go right. And
So,
leave it there.
yeah, we could say Q1 on an X. We're going to just stay in Q1, don't make any change, and move right. Sure, I think that works. Now we need to determine if we are in Q1 and we see a B, what do? We don't want to go into the same state that we were in when we saw an A, because that state is remembering that we've seen an A. So we need to define some other state that says we saw a B. So we're going to do something very similar here. For Q3, we're going to write an X saying that we've seen it, and we're going to move left. But from Q3 now, so we're going to move back. Are we going to see the X? Yes, we should see an X. So we need to define what we're going to do when we see an X. We're going to, just like we did here, move back to Q1. We want to write that as the B that we are remembering, and we want to move right. Does that do it?
Well, you need to accept when you see a blank.
Yes. So accept. We need to, what state do we need to be in when we see that blank?
Q accept.
So we need to see
Oh,
a
like,
blank. What state
from?
are we gonna be coming from?
Okay, so we'd be coming from Q1.
Yes. So if we're in Q1 and we see a blank, then we are going to move to some accepting state, QF. And don't do anything. Doesn't matter which direction we move, we'll say left. And that will be the acceptance. So let's see what we do. Is there anything missing if we go over an example?
Would you want to accept if there's just no A at all in the string?
That's a good question. Remove the first A from a string. So I guess, yeah, we could basically say there is no A, so the string that is left has still removed the first A.
So we could just add an acceptance for Q0.
Yeah, so now if we're in Q0 and we see a blank, then we will move to a UF and say we did it. So that's some other way to do it. Sure, that makes sense. Anyone want to give me a string? I think the eraser has been stolen from this room. I don't see it.
I guess that's just right.
Oh, yeah, it's just behind the water or whatever it is. So let's do this. We have BBB, A, B, A, B. So we would start in state Q0, see a B, write a B, move right. Now we're pointed here. We're still in Q0, see a B, write a B, move right. See a B, write a B, move right. See an A, write an X. So now we're going to, I'm going to keep a separate set of this so that we make sure that we're doing the right thing. A B, 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 X, B, A, B, and we're still pointed at this X. We're going to move right and transition to Q1. So from Q1, we're going to read a B, which tells us that we're going to move to state Q3, write an X, move left. So now we're pointed back at the first X. In Q3, when we see an X, we're going to move to Q1, write a B, move right. So now we're pointed back at this X. In Q1, when we read an X, we're going to write an X and move right. So we're going to move past this X to this A. We're still in state Q1, we read an A. So we're going to transition to Q2, write an X. That Q2 tells us that we've seen an A. We're storing that information embedded in the state. So now we're in Q2, since we moved back left, when we see an A, when we see an X, because that's where we are, we're on an X, we're going to move back to Q1, write an A, that was the A that we've been storing, and move right. Q1 on an X, we're going to move past it. Now we're looking at the B, we're in Q1, reading a B, we're going to transition to Q3, write an X. We've stored that we've read the B. And now we're pointed back at the first X. Q3 on an X says we're going to write a B and move right. We're in Q1, we've seen an X. It seems like there's still something for us to do, huh? We need to erase that last X and replace it with a blank. So Q1 on a blank, we should probably move to some, instead of QF, we're going to move to some basically final state with some last work to do. So the last one we've used is Q3, so this is going to be Q4. We're going to see that blank and move left.
Then just write another blank and accept.
Yeah, well, now we want to on an X from Q4.
Yeah.
So Q4 on an X, we want to move to state QF, write a blank, and now it also doesn't matter which direction we move. So that becomes the QF that removes the last X. So now we get rid of this. And now we have successfully removed this character. We made this string into that string. which is just that first string without the first A. We agree? Any questions about the work? All right, the next one that I have that I'm not gonna go over, I'm just gonna put in your head in case you'd like to work on it over office hours or a while and let me know if you have questions, is adding one to a binary number. So assume that we have some ones and zeros on the input tape. Starting at the very left-hand side, what do you do to go add one, assuming that this is a binary number? So we can come back to this if people would like, if there is time, but I would like to solve at least one of these different types of questions each. Any questions before I move on to the next type of question? Remember, if you're remote and you have a question, rather than type it out, type yes first, so I know a question is coming. So next one would be a context-free pumping lemma. So here we have A to the I, B to the J, C to the I, D to the J. I and J are greater than or equal to 0. Show that this is not context-free. Any ideas of how people would want to proceed with this? Let's just talk about it in the abstract before we start writing it out. How would you approach a question like this? I feel like this is a very relevant type of, I would love to put something like this on the exam.
First thing I would do is try and figure out why it's not context free intuitively first.
Okay. Any thoughts on that? Why is this not context free?
Well, you need one stack to keep track of the I's for the C, and so when you're keeping track of the I's, you can't keep track of the J's or the B's.
Right. Right. So you have a stack that keeps track of all of the A's that you've seen so far. We need to match the A's to the C's. We could put the B's on top of the I's, but the C's are gonna come before the D's. So we need to map the A's that we've seen, but they're at the bottom of the stack. What if I flipped these last two? What if it was A to the I, B to the J, D to the C to the J, D to the I? Is that context free? Yes, it is. Because when you have your stack, you would have your A's, you would have your B's, you would now pop the B's, comparing them to the C's, and then you would pop the A's, compare them to the D's. That you can do with a stack. But as it's written right now, we want to read some A's, we want to read some B's. The only place to put the B's is we can't compare them to the A's. You might know the difference between the I's and the J's. But now you need to take the C's and compare them to something that's not on the top of the stack anymore. And then you need to take the D's and compare them to something that's gone off the stack by the time you need to compare them. So this is not context free for that reason. So let's walk through the pumping lemma. How are we going to set this up?
Go with the boilerplate assertion.
Yeah, so we're going to assert that it's context free. So you would say, assume L is context free. If that is the case, then the string A to the I, B to the J, C to the I, D to the J can be broken down into U, V, X, Y, Z. If we can break it down into U, V, X, Y, Z, we should be able to pump the B's and the Y's. So the assumptions that we know are that the length of BXY has to be less than or equal to M. So we need an example of a string based on M. What is a reasonable string that we could use here that would be in this language? that we think will be an intelligent pick to be able to show that regardless of the V's and Y's that we choose, there is some I that we can pump it to that allows us to generate a string that's not in the language.
A to the M, B to the M, C to the M, D to the M.
Yeah, there's nothing in here that says that I and J are different. Even though you would take a string that would be part of a context-free language, there's still no way to verify that it's in this particular form. Even though you could, if it was A to the I, B to the I, C to the I, D to the I, that would be context-free. But it's still in the language. We need to verify that there are as many A's as C's, and there's no way to do that on a stack, even if there are the same number. So I think this is an intelligent selection. Let's choose W equals A to the M, B to the M, C to the M, D to the M. What does M stand for here? What does that mean?
Like the number of, I guess, nodes or whatever the.
Yeah, there were productions in the grammar. So assuming we had a context-free grammar that represented this language, we have that context-free grammar. The number of productions in that grammar is M. We want to be able to show that for no such M can we write that context-free grammar. We can't write a grammar with one production. We can't write a grammar with 10,000 productions. Doesn't matter what M is, we're going to carry that all the way through the proof to show that no such grammar can exist. Great. This adheres to this language. How do we proceed? We know that this must be able to be broken down now into this string has UDXYZ. What did the U and Z stand for?
They're just like an arbitrary left and right side.
It's the left and right side that gets us to the recursion. We know that since this is an infinite language, there has to be some kind of recursion in that grammar. We have to be able to take some non-terminal and generate that non-terminal again. And the process that happens as we do that is going to allow us to repeat that logic and generate an infinite number of strings. So U and Z are the one time getting to that recursion. So starting from the start non-terminal, going through some number of rules until, let's say that there is some non-terminal B that is represented in terms of some other non-terminals, and now we get to that some other non-terminal that represents something in terms of a B. So now we can recurse and define this B in terms of something that gets to this D that gets to this B. So we create this recursive loop.
So are U and Z allowed to be empty? Or I guess.
Yes.
Okay.
They are allowed to be empty. Because we might have something that's like S arrow something S. I'm not saying what comes before or after this. But now we don't have to get anywhere to get to the recursion. The recursion is built into the start non-terminal. But if we do have some number of rules that there's some number of rules we have to apply now to get to the recursion. So getting to that is what's going to generate the U and the Z. Once we get there, the string that is created, the terminals that are created in a single pass of going from B back to B, that's going to get us the V and the Y. Then getting from this B to the end of the string, that's what's going to get us the X. So now we can see B arrow AB. We just have to, wherever this last B is, replace it with AB. And now we've terminated the grammar. So to produce a string in the language, we have to get to the recursion, iterate the recursion, get from the recursion to some termination where there are no more non-terminals to evaluate. So that's what UVXYZ stands for in this grammar. We know there are M productions. And we know that this UVXYZ must be the case for any string that can be generated by this grammar. So what do we know? We know the length of VXY must be less than or equal to the number of productions in the grammar. How do we know that? Or why can we state that? Why does that make sense?
What it means is that you would have had to have hit the recursion before you pass M characters going from one side in.
So M is the productions. The production, let's say we hit every single production in this recursion. So we have S arrow A arrow B arrow C arrow something D arrow something S. This is the worst case, right? This is as long as the recursion could be, as long as all of the productions in the grammar. We go through all of the productions to go back to the start. If this was to B instead of D, then the number of productions that we use in the recursion is lower than that. So the largest the recursion size could be is the number of productions in the grammar. Does that make sense? We sure? I get some.
I think I get it, 'cause I mean, like you said, like, and this is the number of productions, right? So it means that.
Yeah.
Well, I was thinking from like the regular Common one on like the end and how far you could go, so I'm trying to apply.
Right.
But looking at this, that makes sense, you explain it, it's the length of the recursion.
Yeah, so it's the length of the recursion. There would have to be another production in the grammar in order to make this recursion longer. The longest it can be is this number of productions. So that's all this is saying. To generate that recursion and to be able to get to the end has to be that. So we know that to be the case. We also know that that recursion exists. So the length of Vy must be greater than or equal to 1. There's no way to generate an infinite language if we don't have that recursion. So the length of the recursion has to be greater than or equal to 1. But we're not stating what kind of recursion it is. We could have some characters at the front. We could have some characters at the back. We could have some characters at the front and back. So what that recursion would look like is, let's say this is direct. There's no terminals as we generate this. You can imagine now that going through all of this process just adds an A at the front. Now the length of V is 1, the length of Y is 0, because nothing is getting added at the end of the string as part of that recursion. If the string that we have so far was ABA, and we went through this recursive process, let's say the S is right here. We would add an A at the front of that, and we would not be making any change to the tail end of the string. So length of V is 1, length of Y is 0. V is everything that comes before the non-terminal as we go from that S to the next generation of that S. This would be an instance of iterating that recursion. Right? The only way we're changing the string as we go through all of this is we're adding an A at the front. But this would say now that we could add an arbitrary number of A's at the front. Likewise, if this rule puts an A at the back, now what this looks like is we've put the S here and the A here. So now the variable, as we continue to expand this, the S is going to move out here. We're going to be replacing it with a bunch of A's on the right-hand side. So now the length of V is 0 and the length of Y is 1. You could also do something like this. Now the length of V is 1 and the length of Y is 1. And every time we do this process now, we're going to end up with something like this. Now we have a placeholder in the middle of the string where we can place an arbitrary number of B's in front and A's on the other side. So as we continue to recurse and produce more B's and more A's. So you can see the total length of this has to be greater than or equal to 1, but that doesn't state that the length of B is greater than or equal to 1, or Y is greater than or equal to 1. It's just that as you go through that recursion, we must generate at least one terminal. And that terminal must be on the left side representing a B, on the right hand representing a Y, or the left and right representing the B and Y are both non-empty. They can also be greater than 1. You could have an arbitrary number of terminals here and an arbitrary number of terminals here. The length of V and Y just has to be somewhere between 1 and M. So remember that we're assuming that this is in some normal form where we could break this up into some additional rules as well. So maybe it doesn't make sense for this to be more than a single character, because you can make an equivalent grammar that has just one at the front and one in the back for each of those. But the idea is that could happen at each one of these non-terminals. That would mean that this has to be true. Does that make sense? So there's an equivalent grammar where if you allow for B, 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 S, A, then you could say this is the equivalent to B, E, A, B, F, A, B, S, A. And now you have 3 B's in front, 3 A's in the back, and we've added more productions. Now M is higher, but now you allow for each production it goes to 1 before and 1 after. So now this rule has to be true. Okay, so how do we proceed? Spent a lot of time talking about it. How do we actually proceed?
Find the Y that can break the string.
So we need to consider all possible VY. So we need to now break this down into cases. We need to look at all length M possible places in the string.
So do we need to prove it to be like break the string with every possible case, or just one?
You need every possible VXY window.
Okay.
So we can break this down into the cases where VXY is all A's, VXY is all B's, VXY is all C's, VXY is all D's, VXY is some A's and some B's, VXY is some B's and some C's, VXY is some C's and some D's.
So if VXY is like all A's and you can break it that way, but you can't break it with all B's, would it be considered context free?
No. As it would be considered context free, or at least we wouldn't be able to show via that it's not context free.
So we just don't have enough information if we can't prove it for everyone.
Right. So we need to make an argument for all 7 of these cases that says, regardless of where VXY is, if it is all A's, what do we do to break this string? Well, if that's the case, if VXY is all A's or B's or C's or D's, you can use the same argument. What is that argument?
But there is a little bit of mismatch between your I and your J.
Yeah. So if I add some A's to this, because we know the length of VY is greater than or equal to 2, so you can say, assume that we're going to do this recursion one more time. As we do this, we're going to be adding at least 1 A because the length of VY has to be greater than or equal to 1. So you end up with a string that is of the form A to the M plus the length of VY, B to the M, C to the M, D to the M. In this case, we have a mismatch between the A's and the C's. They're not the same value. M plus the length of VY, where the length of VY is greater than or equal to 1, cannot be equal to M. So we've broken it for this case. You can use a very similar argument to break it for this case and this case and this case. The harder cases are these. What kind of argument is going to work if we have VXY as some A's and some B's?
We do the same thing because there's For like the cases where there's two, it's always gonna be one I and one J, there's not like II or JJ.
So let's look at it. I think that's a great start. So we end up with, so VXY is coming from some A's and some B's. This is gonna break down into further cases, which is kind of annoying. So let's break this string down into the A to the M, B to the M. We know that VXY is over some of this, but what gets pumped? The VXY, because Y can be empty. You could have Vx over here and Y being length 0 over here. So it breaks down into this case, where the recursion is all in the A's. If that's the case, use this argument. You could have it where Vxy is, we have some B's, and then we have the X over here. And then you can again say that you just make sure that you recurse this enough to be greater than this X, because the X is constant, and then we end up in that case. So the important case is where VXY overlaps some A's and B's. So what happens if, I'll again use the A to the M, B to the M part here. What if the B is here, the Y is here, and the X is empty?
Then when you keep pumping A and B, the A's are being mismatched with the C's, and the B's are being mismatched with the B's.
Correct. So that's the argument that you would have to make. So we pump some A's and some B's. As soon as we pump some A's, as soon as we pump some B's, there's a mismatch between the C's and the D's. However you want to make that argument, you can do that. Just make sure that it always works. You're considering every possible case for the length of B and the length of Y here between 1 and M. Does that make sense? How are we doing with that? Maybe some thumbs if you're remote, something out of 10. If you don't want to share it publicly, you can private message it to me. How do we-
For every single possibility, there's an example to break it.
You will probably need to break it down into just about every single case.
Is there an example where one doesn't break it?
Nope.
Okay, so I messed up on the homework.
So yeah, these will all work. And no matter where you put the V and Y in this sliding window, then we want to show that there is some way to break it with some number of repetitions of the recursion. That's either you can choose 0 or you can choose 2, 3, 4, 5, 6. Doesn't matter which of those you choose. For this example, anything will break it, which is why I would throw something like this on the exam and not something significantly harder than this. Because kind of regardless of what you choose, there is a route to the right answer.
So does it need to break it for all I after a certain point, or just the sum I need to exist and nothing matters beyond I?
Does, say that again?
So like, when you find like an I that breaks the string for your VY.
Yeah.
Does it have to be for all I after
No.
that point? Okay.
Nope, you just need a single value of the number of repetitions of the recursion. We historically called that I. I'm hesitating to call it I here because we have an I in the problem. But the number of repetitions of the recursion, you just need to identify one of them for each case, and it does not have to be the same one. So you could set the number of repetitions of the recursion equal to 2, 2, 2, 2, 0, 2, 8. Doesn't matter. You just show that regardless of the number of repetitions of that recursion, when you do 2 here, you end up with something that doesn't adhere to the language. When you use 8 here, you end up with something that doesn't adhere to the language. And that's where you can use constants. It's the constant number of recursions that we're going through. But that works now for all M. So the conclusion that we'd be able to draw from this is that no matter how many productions we have in the grammar M, we break it down into all possible cases. We can now show that none of those cases allow for a string that needs to be in the language, Therefore, the issue was our assumption that this language was context-free. It cannot be context-free. All right, since we have just a few more minutes, I think I would rather spend some time going over the rest of the types of problems. If you would like some additional work on this problem or similar problems, come see me during office hours. I'll be around from 10 to 11 and at least 12 to 1 today. If those times don't work for you, let me know. Next one would be a non-deterministic Turing machine. So design a non-deterministic Turing machine that recognizes composite numbers written in unary on the tape. So composite numbers are just non-prime numbers. How could we design a non-deterministic Turing machine that does this? Because this is going to be really difficult to do with a deterministic Turing machine. But remember that with non-determinism, we can create an arbitrary number of threads. Any thoughts on how we would proceed with this problem? Considering we have 5 minutes, I'm going to let you sit on this. We'll come back to it if there's interest. The last set of questions I have for you are countable and uncountable sets. So first question, is the set of all finite length binary strings countable? If so, find a way to enumerate them. Keep in mind that finite length binary strings can have an arbitrary number of leading zeros. It doesn't have to represent the positive integers in the way that we do in base 2. So 1 is distinct from 0, 1, which is distinct from 0, 0, 1. So the answer is yes, it is countable. The enumeration procedure is we're going to generate all binary strings of length 0, followed by all binary strings of length 1, followed by all binary strings of length 2, followed by all binary strings of length 3. That process will never terminate, but again, you cannot provide me with a counterexample of a finite length binary string that algorithm will eventually output. Does that make sense? All right. Set of all infinite length binary strings. Is that countable?
I don't think so.
The answer is no. Because you can use Cantor's diagonalization on this. You assume that there is an infinite list of binary strings. You can start constructing the next one that's not on the table by taking the first infinite binary string, make it different at the first bit. The second one, make it different at the second bit. The third one, different at the third bit. You continue this process forever, and you're generating a string that is not in the table. That process never terminates, but you're making it distinct from every element in the table, which says that the table is not complete. That such a list of those strings cannot exist. There's no order that would eventually have them all because you're making it distinct from every element of the table. All infinite elements of the table at all infinite positions. set of all languages that are not recursively enumerable. Is that countable? So first of all, what does it mean for a language to be not recursively enumerable?
I just assumed that that informally meant not countable.
Yeah, that's basically what it means, is the set itself is not countable. But can we count the sets that are not countable? So one of those sets would be infinite length binary strings. Is there a way to generate, write an algorithm to generate the languages that are undecidable? Yeah, the correct answer there is no. Because if you could do this, then you could actually enumerate any of those languages. You could use diagonalization, the way that we showed, not Cantor's diagonalization, but our method of enumerating something like the rational numbers, to be able to say something like, all right, I'm going to take the first element of the first set. I'm going to take the second, and the first element of the second set. I'm going to take the second element of the first set. If there was a way to enumerate those languages, then we could weave through that to be able to enumerate all of those elements. So if we could do that, then we could enumerate the elements of those sets. Since we can't enumerate the elements of those sets, then languages that are not recursively enumerable cannot be countable. So I like to throw intuition-based questions like this on exams because it's not just, did you memorize this idea? It's, do you understand it well enough to apply it to a problem that you haven't seen before? I'm not necessarily saying that I will do that this time, but I like to try to find ways to really test your understanding of something.
If we get a question like that, does that have to be like a formal proof?
No, it would be okay if you came up with just the intuition behind it. Yeah, I'm not looking for formal proofs at this point, but I want to see that you can take an idea that you have seen and reason about it. In a graduate level class, I probably require a proof, but this is not a graduate level class. I don't think it's worth it. You're not trying to prove this mathematically to everyone, but I think that as a working adult, you want to be able to solve complex problems and you want to solve them using tools that you have seen before. So this is what trains that part of your brain. You learn something and you want to be able to apply it when you see a similar problem that's not the exact problem you used it on before. That's an abstract skill, but it's an extremely useful skill everywhere. So I like to try to train that in my classes. We are already over time. Does anyone have any last minute questions on any of these? All right, I will throw this set of slides up on Canvas. I will throw this lecture up so that you can look back over it. And if you don't have any other questions or I don't see you in office hours, then I will see you for the exam tomorrow. Remember that you can also submit a rewrite for homework 3 up through end of day tomorrow.
Can I submit over the ones I submitted last night?
Yeah.
Okay.
I'll look at the last one that's submitted before midnight tomorrow. See you all for that.